arrows, and undirected graph, which do not have any arrow. For undirected graph, we assume that it is two-way. For example, in Facebook, this is a person A, another person B. So the H can be friend. So A is a friend of B, B is a friend of A. It will be two-way. For the directed graph, we can also subdivide it into two divisions. One is the cycle. So let's say this is the start. A node can return back to itself. So it is cycle. Example, A can return back to itself. A, go to B, go to C, and go back to A. So what do you think? What kind of problem do you think that use the cycle, directed cycle? Loop. Okay, yeah. So you need to perform things in one loop. Alright. So let's say you need to do some traveling. So at first you will go to the first destination, and then you go to the second destination, and then you need to go back to your home. So this is one example of problem that can be solved using the cycle. Actually, cycle is not like the method to do the solving. It's just to represent the problem. So we can see here that, you know, although we start from B, then we can go back to itself. There is also problems whereby when it represent in graph, it become an acyclic graph, which means this graph is without any cycle, thus cannot return to the original nodes. Okay, so for example, you want to send one parcel to somebody. Okay, so this A can send the parcel to B. C can send parcel to B, but B cannot be sending to parcel to anybody. C can send the parcel to A. So in this case, C won't be receiving anything, but because what they can do is to go to this direction. Okay. Exactly the same, the directed weighted graph. Okay. Undirected weighted graph and also a cyclic weighted graph. So we have the weight here. So this weight can be, like I said, can be cost, distance, any parameter. Okay. This is an exercise to see whether we can proceed to the next, to elementary. So can you name me what is A? A is undirected graph. Okay, good. What is B? directed graph. Good. C. Okay. C is weighted directed. Directed weighted graph by Kishore. Weighted. Okay. You need to answer. Okay, you need to answer. Let's see here. The answer A is undirected graph, correct? B is directed graph, correct? And C is directed weighted graph. Okay, so you need to make sure it is full. Okay, Aiman. So good try, everyone. So I think that's the end of the graph theory. Good, good. Alright, next, chapter 22, elementary graph algorithm. So for the elementary, we can divide into two. Okay, so I will just explain the first part, which is the representation of graph. Now, how we want to represent the graph in a so how we going to represent the graph is there are two ways to represent the graph. One is adjacency list and two is adjacency matrix. So either way is applicable to directed or undirected graph. Okay. So this is how you want to, I think, to implement the graph. Okay, so let's say we have the directed graph such as this, and we want to represent adjacency matrix and also this adjacency list. So for us to do the matrix, right? So let's say here. How we want to represent this in matrix? We can see that first step, you see how many vertices are there. Okay, so we have 1, 2, 3, 4, 5. So what we do, we build a matrix that have 5 and 5. So we can, since this is directed graph, that there are arrow. So we can see that 0 can go to 4. When you do this graph, right, this is to, sorry, this is from. And this is 2. So you are from 0 and you can go to 1. Okay, so 0 to 1, you put 1. So from 0, so this one is done. From 0, you can also go to 4. So 0 to 4, here you put as 1. The rest you put as 0. Next, from 1. 1 can only go to 3. Can 1 go to any other direction? No, right? So the rest we just put it as 0. Next we do the 2. 2 can only go to 4. 2 can go to 4. The rest 0. 3 can go to 2. 3 can go to 2. And 4 can only go to 1. The rest will put 0. So we have completed our matrix. Simple, yeah? Next, if we want to read our graph into adjacency list, into a list, okay? For list and matrix, right, they are pro and cons when you want to do the implementation, okay? But today I'm just going to teach you on the theory. Right now, you can see that 0, 0 can only go to 1 and 4. So can only go to 1 and 4. 1 can only go to vertex number 3. 2 can only go to vertex number 4. 3 can only go to vertex number 2. And 4 can only go to vertex number 1. Okay, so we are able to complete our list. So in your tutorial, you will need to present your graph in these two methods. So this is four-directed graph where there are arrows. For the undirected graph, as I said earlier, it can go both ways. For instance, here, let's take a look at, let's do 0, vertex 0 first. This vertex 0 can go to 1 and 4. So vertex 0 can go to 1 and 4. But vertex 1 can go to 0, 3 and 4. Vertex 1 can go to 0, 3 and 4. Vertex 2 can go to 4 and 3. That's why it's 4 and 3 here. 3 can go to 1 and 2. 3 can go to 1 and 2. And lastly, 4 can go to 0, 1, 2. 0, 1, 2. Okay. So let's say 4 can go back to itself like this, then we can put here as 1. Okay, in this case. But that is not the case. So same as doing the list, 1 can go to 0 can go to 1 and 4. 1 can go to 3 vertices. 0, 3, 4. 2 can go to 3 and 4. And 3 can go to 1 and 2. The last vertex 4 can go to 0, 1 and 2. Okay. Question from Farhan. Should row always be from vertex and column 2? As far as I know, yes. That is how it is. But let's say you want to change, right? Because you are the one who going to manipulate the data. So you make sure you know which one is it. Okay. From Kishore, Doctor, we also have weighted adjacency matrix, right? Yes. For weighted adjacency matrix, we need to put we need to indicate somewhere on the weight. Okay, but for this course we exclude that. But of course you can see how it can be done. Okay, to put the weight somewhere. I read it just now. Is at page is at section 22.1, right? Okay, so this is how you're gonna present the graph. Okay, now we have completed the list and matrix. Now we're gonna dive into the systematics. We call this traversal. Remember when we were doing BST, we want to traverse, which is to visit every nodes. So even for graph, we do have algorithm to do the traversal. So given a graph, so graph is G, V, and E. So these are all the vertices and edges. Systematically explore the edges of G, edges of the graph, to discover or to traverse every vertex that is reachable from S. S is the starting point. In this lecture, we will learn 3 graph traversal techniques, which are the depth first search. Later, I just call this as DFS, breadth first search, BFS, and also the topological sort. And for each of these techniques, they are the use of it. And in this lecture, we're just going to discuss one usage. Okay, and from there you can try to explore more. So let's learn about the DFS. For the DFS, this is the algorithm. Okay, like I said, for DFS, we want to visit all of the vertex. So let's say you want to become a traveler and you want to visit the entire world, all of the countries in the world. So in that case, your vertices are all the countries in the world. Okay, so you can use the depth first search to make sure that you visit all of them. However, for the depth first search, you can use the depth first search when you need to make sure that there's like the connectivity. Let's say you want to travel the entire world, but between Malaysia to United Kingdom, maybe there's no connecting flight. So depth first search is a suitable algorithm to resolve connectivity problem, because it makes sure that we get the shortest path. At the same time, it is connected. So for instance, for those students from network department, so you can also use this to resolve the routing, okay, for your package. The concept is a traversing method used to stack uses the stack. Okay, so now you are still using the data structure method. Okay, and we use the stack for storing the visited vertices. So DFS is the age-based method and work in the recursive fashion. Why is age-based method? Because it want to make sure that they have the connection between all of the root. So DFS is used in directed graph, of course, because connectivity problem needs to have directed graph. It needs to know the direction. Well, we can also use undirected graph because we can assume that, okay, we can go back and forth, okay, but most importantly, DFS can use the directed graph. So to search the path between every pairs of vertices. To explain the algorithm, we try to understand the algorithm using illustration. So this is the example of graph. Okay, in this graph, it is undirected, so we can know that it can go both ways. In order to do this, we need to make one assumption. It is that as much as we could, we need to follow the alphabetical order in order to get the shortest path. So in here, we should be from A, we should be going to B. But however, there is no H between these vertices. Therefore, we need to settle for less. So since we need to use stack, so this is our stack. We start at S. So the question is, apply the DFS to the graph given and give sequence of visited vertices. So this, we start with A and we put it in the stack. Next step is you check the unvisited vertex from A. Okay. So from A, where can we go? We can go to C and we can also go to E. So since we can go to C and E, we put the C and E, we push it in the stack. Okay. So if you remember in your data structure, for stack we can push and pop, right? Am I right? Push and pop. So we push C. And we also push. So currently the sequence of visited vertices is A and C. Next, hold on. So following the alphabetical order, because remember we make the assumption earlier, if we use alphabetical order, we can get the shortest path in this problem. So we take C instead of E. So currently, the sequence of visited nodes is A and C. Next, because for DFS is related to the connectivity. So since the last vertex that we visit was C, so we check what is connected to this C. We can say that C is connected to B, D, and F. So following the alphabetical order, we need to push B into the stack. So currently the sequence of visited vertices is A, C, and B. I think if you understand this, then you should understand the rest of the BFS. Next, from B, we need to check the unvisited vertex. So B is connected to C and F, but the rule is to check the unvisited. C we have visited. Therefore, we only have one choice, which is F, to be pushed into the stack. Next. Okay, can anyone tell me what is next? What do we need to check? Kishore. From F.
So first we have to check all the vertices that are connected to F, and those vertices must be unvisited. So vertices that are connected to F and unvisited, we have D and E. So we have to choose the vertices in the least alphabetical order, which is D.
Okay, so we will choose D. Okay, try to continue.
And then vertices that are connected to D, we have C and F, but they have been visited. So E, but E is not connected to D.
Yeah, E is not connected to D. So right now, since okay, so check the unvisited vertex from D. There is no unexplored edge leaving from the vertex D. Okay, Kishore is right. So right now, we need to pop out the D. Although we pop out the D, right, the sequence is still A, C, B, F, D. So right now our stack is not the same as the visited vertices. So we need to check the F. So F still have unvisited vertex. If F already have visited vertices, then we need to pop F. But in here there is one which is E, so we need to push E into the stack. Okay, next we will. So this is our sequence A, C, B, F, D, E. Okay, but our algorithm, if you look at the algorithm in the few slides before, the algorithm will not stop. Okay, the only stopper in this algorithm is when all of the elements are pop out from the stack. So what we need to do here is we need to check if there's any unvisited vertex from E. There's no, right? there is no unexplored edges leaving from vertex E, so we need to pop out the E. So we pop out the E. Then we repeat all of the vertices. Okay, so right now empty stack signal the algorithm need to stop. So F all visited, B all visited, C all visited, and A all visited. So the algo stop. Okay, so this is the DFS. So let's say these are the countries, right? And maybe and the H is like the connecting flight. So we can say that in order to travel all without any transit, we need to travel from country A, C, B, F, D, and E. So this sequence can also be drawn as the following. So at first you travel from A, then go to country C, B, F, and then go to D. And then from go to D, and then only you need to go to the E. This is the last result. Okay, so we can see that these are all connected, and I'm not so sure if in real life we need if we are talking about the flight, right? I'm not so sure if we need to return to the F or not. But after we go to D, then we need to decide to go to the F. Okay. So those are the sequence. Next is BFS. For the BFS, we will use Q instead of the text. Okay, and the real life application is in here we can find the shortest path between two vertices. Okay, to illustrate all this algorithm and description, you can reread the description after you understand the example. Okay, inshallah you can understand better. So this is Q, is used to keep track on all the unvisited vertices using BFS. Apply BFS to the given graph and give sequence of visited vertices. So it starts with S. In some questions, if it does not state anything, right? Of course you can start with 1 or A. Okay, but sometimes if it's just talking about the countries, then means if it's not stated in the question, means you can start anywhere. Okay, so in here we declare A as the root. The same, we assume traversing vertices in alphabetical order will find the shortest path. So we will start with A. Okay. Next, we need to check the unvisited vertices from A. Okay, this one still the same as the BFS. Now we know that it is C and E. So instead of just choosing C, we are going to Q, C, and E and DQ the A. So we QC, we QE, and we DQ the A. Okay, when we DQ, because this one is Q, it does not pop, it will DQ. Okay, here. So means we have complete the A. Next, we need to check the unvisited vertex from C. Okay, C. The unvisited one is B, D, and F. So we are going to queue B, D, and F. Next, we will dequeue the C. So we visited A and C as for now. So next, which one should we check? The F or the E? Remember Q in your data structure is first in and first out, right?
Check E.
Check E, okay. So check E. E can, for E, there is no unexplored edges leaving from the vertex because A is already visited. F we can consider is already in the, we already queue the F. Okay, so since we have DQ F, so V we can DQ the E. So it's considered that we have visited the E. Next is we check the B. So again, B should be able to, the H is to C and to F. Okay, C we already visit, F is already in the queue. So we can just dequeue the B. Next, we check the D, since D and then no unvisited, so we dequeue D, and lastly we dequeue the F. Okay. So again, empty queue signals the algorithm to stop. So the output in order, the shortest path will be first from country A go to country C, then go to E, then go to B, go to D, and go to F. Okay, I just realized something. Okay, correct. So this is BFS. Still, when we use graph, we can see that for the shortest path, there's some cons in graph because it follows the flow. So we may not really be able to get the shortest path because from we need to always follow this queue. We cannot reconsider the entire thing again. So that is why dynamic programming will be able to improvise the graph in that sense. Okay, because later in dynamic, it won't do in sequence because right now when we do the B, right, this is the turn for the B, okay, to try, and then we still need to visit the B, although it is nearer to actually visit the F. Okay, so this is the limitation of graph. So I hope you'll be excited to learn about the dynamic programming. Give you some introduction. Okay, so lastly is the topological sort. Okay, so for the topological sort is also traversal, where we need to visit all of the vertices, but the purpose is slightly different. Okay, so topological sort takes directed acyclic graph. Okay, means it cannot return to itself, and to produce linear ordering. Let's say you have a graph and you need to identify the ordering, where to go, but there's like some constraint. Okay, for instance here, there's some constraint that the arrow is the constraint. Okay, for example, you need to pass the data structure course in order to take the algorithm and analysis course. Okay, so the prerequisite can be identified by the topological sort. So later we will learn about how to use the algorithm, but for now, the topological order for this graph. Okay, so in naive, right, we say that okay, first you need to take Java. Then when you pass your Java, then only you can take data structure course. Then when you pass, then only you can take the algorithm analysis and design. Let's say this is what the rule in your program handbook. Okay, so the ordering will be Java, data structure, and then algorithm analysis and design. Of course, when we have this graph, okay, it is easier for us to determine this. But let's say we have a huge graph, okay, and it is they have different orders, so so we can use the topological sort in order to indicate which one is the event that need to be happening first, and then followed by the rest of the order. Okay, so how are we gonna do this? In order for us to do this, you can watch the video, but let me explain this to you. So let's say this is an acyclic graph. Okay, so you see A cannot go back to itself, B cannot go back to itself, and you need to know sometimes graph can consist of acyclic and cyclic graph. Okay, some of them can, but in this case, no. So let's say this is still the course. Course A, you need to do course A first, then only course B, then H. Okay, and this H got two prerequisite. In this D needs to be happening first. So this is the event. So it get quite complicated to know which one needs to do first. Which course should you take first? Okay, so the first way is to find the final vertex of a path. Okay, by checking if there's any no unvisited neighbor. Then push the vertex into the stack. Okay, for the topological sort, it's like the DFS. We use stack instead of queue. So we will start from A. A, we will need to check A can go to B. Okay, B can go to H. And then for the H, right, it cannot go to anywhere else. Okay. So H has no unvisited neighbor. Okay, so H can This one is the neighboring, but you know there's no way H can go to the D. Okay, so this is the end of this acyclic graph. So we put H in the stack. Then we check the B. B has no unvisited neighbor. Okay. First of all, B has unvisited neighbor, but now B cannot visit anywhere else. Okay. So we put Can you see my screen? We put B in the stack. Okay, next we check the A. A can still visit F. So then we check F. So F got no way to visit. Therefore, we can put F in the stack. Next, we check the A. So A has no unvisited neighbor. So we will put A into the stack. Okay. So even at this stage, to appreciate the topological sort, we can see that this is the ordering. For example, you want to take the cost, right? Which one you want to take first, right? So this will be the ordering, okay, from the bottom. But let's just continue. Here, Chan Joey, where should we visit next? Which vertex? Okay, if there's no, it's not mentioned, what are they? We can just follow the alphabetical order. Okay, since now C has no unvisited neighbor. So currently C cannot be visiting any other. So we can put C in the stack. Next, we do the D. Let's take a look at D. D can go to I and E. Since we are following the alphabetical order, we will use D and then go to E and then I. Okay, so we have D, E, and I. So between E and I, A, B, C, D, E. Okay, because right now we need to use this flow D, E, and I. Okay, so we need to check the last one. I has no unvisited neighbor, so we can put I in the stack. Then we check E. Right now E has no unvisited neighbor. Then we put E in the stack. And then after that, now D has no longer unvisited neighbor. So we can put D in the stack. We are done here. Next is between G and J. G comes first alphabetically. So over here, G has no unvisited neighbor since A and C is already visited. So we can put G in the stack. And lastly, we put J into the stack. So the topological ordering for this graph is J, G, D, E, I, C, A, F, B, H. So let's say you want to take your course, right? Lastly, you take the H. Okay. Of course, because this is graph, right? They don't reconsider. They always use the sequence. So this sequence can be, there's some tendency that this in between this can be switch. Okay. All right. Understanding this, let's try to do this together. How we get the topology ordering from this graph from to take Java first, data structure, algorithm, design and analysis. So I will give you 5 minutes to do some drawing like this, or maybe you need 10 minutes to do some drawing like this, and then you paste it at the chat function. Okay. So now is 4:09 to 4:10 to 4:20. I'll be away for a while. Please paste your answer, yeah? Okay, let me know if someone can explain. Any volunteer? So can okay, yeah, can you explain? Share your screen.
Need to share screen.
Yeah.
No, just like this. So you check if there has any unvisited nodes around him, then found data structure. So then data structure is there any unvisited node in the I mean what's behind it, and go to algo. And is that algo no any unvisited nodes anymore? So we just push it to the stacks, and then we'll check the previous one. Since it already has no unvisited nodes around it, then we go to data structure. So data structure also has no unvisited vertex around it, so we push it to the stack, and finally Java.
So the order will be read from
Java to algo.
all right, okay. Thank you.
Welcome.
Okay, lastly, we will learn about the minimum spanning tree. Okay. All right, so thank you, Kishore, Yap, and Munir for submitting your answer. Okay, on graph, we also be learning about the minimum spanning tree. Let me know if you cannot see my screen. So remember in the beginning, I said that we're gonna, for the graph algorithm, we're gonna learn about the elementary. So we have completed all this. So we move to chapter 23, which is the minimum spanning tree. So for the minimum spanning tree, we have the prim, we are going to learn only two algorithms, Prim's algorithm and Kruskal algorithm. So minimum spanning tree is a spanning tree that has minimum weight than all other spanning tree of the same graph. Minimum weight can, because it's always find the minimum. So two most popular algorithms for MST are Kruskal's algorithm and Prim's algorithm. So let's try to refresh our mind. Greedy algorithm, as the name suggests, always make the choice that seems to be the best at that moment. Okay, so we can relate it to the minimum spanning tree. Although for a greedy algorithm, we do have the maximization problem or minimization problem. But for the minimum spanning tree, as the name suggested, we always try to find the minimum. So it's only minimization problem for MST. Okay. So here we have the prim and here we have the Kruskal. Just to give an overview what's the difference between the two. So we have a graph. Okay. When we have a graph for the prim, we always need to choose the shortest edges from the visited vertices. If the vertex is means it needs to have connection with the visited ones. Unlike for Kruskal, to me it's quite simple. We just choose the shortest edge. Whichever the shortest, then we will choose that. So if we look at this, it is a greedy strategy in graph theory. Okay, so MST adopt greedy, but just for the minimization problem. So we are going to look at the Prim's algorithm. But in short, just summarize it here. First, we need to select the root vertex. It can be given in the question, developing a software from, okay, and we need to select the shortest edge connected to the visited vertices. Then we generate the minimum cost spanning tree starting from the root node. In MST, we still need to visit all of the nodes, and that's the rule. And when we visit the node, we will get the minimum cost. So let's say this is the given graph, and what you need to do is you are a traveler and these are the country that you want to visit. Using Prim's algorithm, you will still need to visit all of them, but in what sequence will give you the shortest path. So in here you can choose a vertex, okay, if it's not given. But if it's given from the questions, then you need to start from the chosen vertex. So in here they start from this vertex. So from this vertex, choose the shortest from this vertex. So you want to start from here. So we can have 3 and 2. We choose the shortest edge, which is 2. Now we are here. Okay. When we are here, you can choose 4, 3, 1, and don't forget you can also choose this edge. Okay, because the rule is it needs to be visited. So this first vertex is already visited. Okay, and this is the second. So we have 1, 2, 3, 4. 4 options inside here. So usually one of the way is to write down 3, because we can have this 3. Okay, so between 2 and 3, we choose 3. Okay, so we choose 2. So we are here. So over here, we can go to 2, 3, and also 4. Okay, so over here we can see that 2 is the shortest path. Therefore, we will go to 2. When we go to 2, from here we will have new path, which is 4. So don't forget to write, we have another 4 here. Okay, so now we can see that we have 3, 3, 4, 4. For Prim's algorithm, you can choose either one. Okay, so we are up to here now. So in this, they choose this particular 3. So it will go to 3. now cancel one of the trees. Okay. So when it reach here, we can also go to this path. 1, 2, 3. Okay, but in this example, it will go to this. And then from here, right? Why can't we go to here? Okay, we have 4, 4, and 3. Why do they choose 4? It's because there's one condition for MST, we cannot have cyclic graph. Okay, so therefore we will go to so we cannot take this 3. If we take this 3, it will be a cyclic graph. So we need to take 4. Okay, so done. So after we have here, then we can calculate 2 plus 3, 5, 7, 10, 14. So our MST for this graph is 13. Okay. So you see, the rule is you need to visit all of the nodes and it cannot be cyclic. And thirdly, for prim, they have additional condition. We can only choose vertex that is from the visited nodes. So this is prim. Okay. So over here, oops, I already give you the answer, but can you, I'll give you 10 minutes to do it your own to get this answer, the given answer, and one of you need to explain about how you get this answer. So I give you 10 minutes to do this exercise. For 27 to 4:37 Prince Elko. So you need to find the total length. Okay, I'll be right back. So those who, if you have complete, then you can paste your answer, and I really hope that you can try to explain, okay, in order for us to complete today's class. Okay, anybody can help? Do you get the answer given? Any volunteer? Okay, why don't we do together? Okay, you just tell me. Alright, so let's say we are going to start from A. We are going to start from A. So what are the choices that we have?
Three choices.
Okay, what are
10, 19, 15.
So when we reach C, we have additional choices here, which are 14 and 16. So we just write 14 and 16. Now we need to compare 19, 15, 14, 16. Which one is the smallest?
14.
14. Thank you. So 14 will go here to the F. So when we reach F, we have additional 3 choices. Therefore, we just write down. We have 5, 6, and 9. And of course, again, you need to consider from the beginning. And then we pick the smallest, which is 5. So we will go to I. Okay. Okay, hold on. I take different color. So we have done this one. G. For G, we cannot consider this 9 because if we take this 9, it will be cyclic. Okay, so the choices that we have is, so we can cancel this 9. We cannot wait. Okay, the choices that we have will 3, 3, 24, and 11. And 11. So we pick the smallest, which is 3. right? 3. Then this. Okay. Let's see what we have. 4. We already visit 5. 5 of them. Okay, so when we reach here, we reach D. We cannot have this path because it will be cyclic. The new choices that we have is 17 and 12. So we just write here 17 and 12. Okay, so we consider which one is the smallest. 4 is the smallest, right? 4 is the smallest, so we traverse this. Okay. Next, we get new option. This one is okay to go to J. It still will not be cyclic. Then here, so we have 2 more feasible solution. So we just write here 2 and 13. And when we compare all, 2 is the smallest. So we can travel to J. Okay. So this is 6, this is 7. Right now we can see that so we check for the smallest. 6. Okay, 6 is the smallest, but we cannot do 6 because it will be cyclic. So we cancel this. It's okay lah. I just cancel 6. Is it 11 that is the smallest? Seven. Okay. So 7. Okay, yeah. From D, did I write 7? 7. Oh, I accidentally write 17 is 7, right? Am I right? Yeah? Okay. Because I wrote this 7 and 12. So now 7 is the smallest. Therefore, we will traverse to P. So this is our 8. Okay. So right now, we will need to see the smallest, 11. We cannot do 11 because it will be cyclic. So we cancel this. Then we see 12. 12 is here. Okay. Number 9. Alright. So we check to see that we already cover we visited all of the vertices. Next, we can calculate the length. Okay. Yeah, so this is 1, 1, 2, 2. Just check if it's the same. 4, 5, 6, 7, 8, 9. Okay. So since we get the same answer, then we just sum up all of this. Okay, then we will get total of length of 58. Oh, I see somebody paste the answer. I should have asked you to explain. Oh, thank you, Yao Ming. Smallest is 10. Smallest is 14. Okay, so you can copy Yao Ming's answer. This is like for you to do the revision. Okay? Okay. Now, lastly is the Kruskal. So this is the algorithm. First one, we need to select the shortest edge in the graph. Then, second, we select the next shortest edge in the graph without having to consider the connection. Lastly, we generate the minimum cost. So, in here, simpler. Alright, so given here, we search what is the smallest. The smallest would be 2, right? So in this case, they take this. This is the smallest. Then we try to find the smallest again. So we have 3, 4, and 2. Since 2 is the smallest, then we visit this vertex. Then we have 3 and 4. These 3, we can also take this. Okay, the reason why this question take this because they want to show that, you know, without any connection, you can also visit. Okay, so for Kruskal, right, to illustrate is something like you need to visit all of the countries, but it may not be you are like the only person. So maybe you play a game with your friends in UK, then you say that, okay, this year, this is what we're gonna do. We're gonna visit all countries in the world, but collaboratively. Okay, I visit 3 countries, you visit the other countries, and after that we merge, and maybe you want to take pictures, so we merge all of our pictures. Okay, so maybe you want to do some YouTube channel. You can use Kruskal to identify the sequencing. Okay, so once you get the sequence, then maybe you can dedicate. Alright, so we will take 3. After that, there are also 3s. Okay, so you can take either these 3 or these 3 as long as it's spanning tree. Then you can calculate 2 plus 2, okay, which means you get 14. So usually for Kruskal, the cost will be lower. Alright, so since we only have 5 minutes, we're just going to go through this together. So from here, it won't say that they won't pick any vertex in this question, okay? So here, we can try to search for the smallest. So the smallest here is 1. So 1, it can travel here. So in here, right, you can say that F going to I or I equal going to F. Alright, then next, you just choose the next smallest. From this vertex to this vertex. Okay, so this is the first one, and this one is the second one. Then we see there's 3. 3, 4, there's no 5, straight away 6. 6. Okay, 7 we need to skip, okay, because otherwise it will be cyclic. 7, 8. Okay, then we can do the 8. But if we do this 8, it will be cyclic. Okay, so we cannot 8, then we should do 9. This is 9. So we have visited all of the nodes. Okay, so this is Kruskal when six. So even for the same given graph, you can implement Kruskal or Prim, but in this case they are different. Okay, and we always find that using Kruskal will have lesser length. Okay, so that's all the lecture today. I hope that you enjoy learning new algorithms and try to relate with the real life problem. Okay, like this one, since it is not connected, so maybe you can delegate, do the delegation. How about the tutorial class this week? Okay, for tutorial class this week, we will firstly do asynchronous, like because it's public holiday, and then we're gonna discuss tutorial 10 and 11 on the next week, because next week is is a break, right? 1 week, so we're gonna discuss in the following week. But of course, I still want you to answer the tutorial question within this week. Okay. So okay, all. Thank you so much for your attention. So for those who are celebrating Selamat Hari Raya, okay, and to all of you, I would like to apologize if there's any lacking on my side. Okay, I'm also learning. Alright, bye all. Thank you for your participation. Bye.
Thank you, Doctor. Bye.
Thank you, Doktor. Selamat Hari Raya.
Thank you, Doktor. Selamat Hari Raya.
Thank you, Doktor.
Welcome.
Raya.
Selamat Hari Raya.